So our first invited speaker is Philipp. He has already a very rich career in a PhD in Utrecht, and then postdocs at Perimeter Institute and the Institute for Quantum Optics and Quantum Information in Vienna and University College London. And now is assistant professor at Okinawa Institute of Science and Technology. So he'll be talking about complementary identities. Over to you.
Yeah, thanks very much. And let me start by thanking also Philipp for inviting yet another Philipp. It's definitely the most Philipp conference I've been to. So the title is actually somewhat misleading. It won't be very much about complementarity identities. At the end, maybe we get to it. But I didn't have in the end a better title anymore, and so I just stuck with it. But yeah, it will be mostly about a reconstruction that I was involved in a couple of years back. So here are the main references. It's actually a two-part reconstruction. It's only the package together that does it. There's also some reviews here. And in particular, in this talk, I would like to put that reconstruction, or also somewhat more generally, the reconstruction program somewhat more into perspective, in particular in relation to, for instance, axiomatizations of special relativity. So it's very nice that Philipp talked about it earlier today, because I will directly connect with that, but I will in fact also connect with some of the things that the other Philipp has said. Anyway, so let's get started. And then later on, I will tell you, so I will do this more at a qualitative level at first, and then I will tell you a bit more about the reconstruction itself, some of its ingredients. So yeah, the prelude is the relativity principle, or a special relativity principle, which colloquially speaking reads as that all the laws of physics should be the same in every inertial frame. And that's a nice, somewhat intuitive principle. And what is nice about it is that it really implies all the counterintuitive phenomena of special relativity, such as relativity of simultaneity, time dilation, Lorentz contraction, and so on, really just qualitatively by basically accepting that axiom. And in particular, you can get something like the relativity of simultaneity, which, by the way, is implies the relativity of or the Lorentz contractions and time dilations. You can get it really at a qualitative, intuitive level without any equations. And here, in fact, I take this relativity principle to also imply the constancy of the speed of light across different observers. So, and that's because the Maxwell equations are part of the laws of physics. They should be the same in every inertial frame. And so I shouldn't be able to distinguish. So the speed of light is, of course, part of the Maxwell equations. And I shouldn't be able to distinguish the different inertial observers according to the speed of light that they ascribe. So for me, I take that as implied by this. Now, if you take the speed of light to be the same everywhere for every inertial observer, then you can have these cute little thought experiments of some train racing along, and then maybe you have Alice on it, and she stands right in the middle of the train, and then she sends for her simultaneously two light signals to the front and the back, and in such a way that for her, there's two detectors and they're equidistant, and for her, the detectors will click sort of simultaneously, just because the speed of light is the same in both directions. But then for Bob, an observer outside, relative to whom this train is racing, if you then also take into account that relative to him, after submission of this light signal, the detectors actually move, but yet the speed of light is the same, then it is clear that relative to Bob, for instance, the light signals hitting the detectors won't actually happen simultaneously. So it's something that you can, it gives you a very intuitive explanation of something that seems at first very counterintuitive. And so that's, of course, part of the beauty of this setup, and maybe also one of the reasons why there hasn't been so much debate about the interpretation of special relativity. And now coming to the question of Wheeler, why the quantum? As you all know, of course, in quantum theory, the situation is quite different. A priori, we have these somewhat operationally obscure textbook axioms to define the theory, and also otherwise we would have been standing here. It has evaded a commonly accepted interpretation. And then there were a couple of people who wondered whether that's related. And in fact, it's also nice that Philipp presented exactly those quotes by Rovelli, Zahlinger, and also Chris Fuchs, who were suggesting that maybe we should try to find an a similar operational axiomatization of quantum theory to maybe try and remedy the situation. And in particular, can we find an axiomatization that also in some intuitive sense maybe gives us an explanation of the counterintuitive phenomena, entanglement, and so on and so on. So that's the setting in which we're going to be working. So as with special relativity, you would have to find somehow a landscape of mechanical theories and then some axioms that single out special relativity within it. So we would want to do something similar here in quantum theory. And so the basic idea is, of course, first of all, to somehow, we know where we want to get to at the end, but for a while, just forget about the textbook formulation of quantum theory, and then define some landscape of alternative operationally meaningful theories. Often it's generalized probability theories. Here I won't actually be doing that. And then you try to find some kind of operationally motivated axioms that somehow single out this blue dot within that landscape. And one thing to notice that generally in any of these axiomatizations, the distinction between what are the axioms that actually define the landscape and what are the axioms that single out the theory you're interested in within that landscape is always a bit blurry. So that's just in the nature of things. That's just one thing to keep in mind. And now, when we think about such an axiomatization, for quantum theory, you could put up a wish list or some hopes that we might wonder whether they could be realized here. And in fact, one question could be, could we have axioms that are in some sense as intuitive or simple as the relativity axiom so that we can somehow just all accept that? A second one is using those axioms, do we get, was already alluding to that before, some intuitive explanation of counterintuitive phenomena, in some sense similar to what I did with the relativity of simultaneity without even invoking much formalism. And a third question is, is there any chance that we can settle the interpretation of quantum theory? Does a derivation from a particular perspective single out maybe one interpretation or types of interpretations as being the right ones in some sense? And then we can even ask another question: can a reconstruction of quantum theory maybe give us even something new? So maybe some new predictions or new structural insights. What I mean by that is not just a new formulation of quantum theory. And in fact, most of these reconstructions give you, in some sense, a new formalism for quantum theory, be it, for instance, the categorical quantum mechanics or also IGPTs, or also what I'm going to be talking about. But those are just different formulations of the theory that's already there. And so here the question is more about, can we actually get really new structural insights that we can also formulate using the usual formulation of quantum mechanics, new kind of predictions, and so that it really tells us, opens a new perspective on the theory and tells us something new that we might be able to use in some say quantum information applications or something like that. So and yeah, as most of you know by now, there exists actually many successful reconstructions that all started with Lucian Hardy in 2001, and then there's been a whole sequence of reconstructions, and I'm not even mentioning all of the names that have been involved in this. And we can now ask the question of how do these reconstructions actually fare against this wish list? And now I'm not the representative of all of these reconstructions, and that would also take us way too far. So what I'm going to do is I'm going to discuss the reconstruction that I've been involved in and compare it to that wish list. And then, representatives of other approaches can do that maybe too. And yeah, so here is the very basic setup of the reconstruction. Just in a nutshell, that I'm going to be talking about. So this is quite colloquial, what I'm going to tell you about here in the slides. I will tell you a bit more afterwards, after we've done a qualitative comparison. So I hope some of this will become clear a bit later. But the setup is here. First of all, we're only going to reconstruct a quantum theory of n qubits, arbitrarily many. And we're going to model the whole process here by basically some prepare and interrogation setup. So we, in some sense, we can think of there's a preparation device, that spits out some systems, and there's an observer O who's interrogating the suspects or the system with some questions, and here we will only be allowing binary questions. So yes, no questions, and the reason I want to do this is because we want to develop a universal framework for quantum theory, which doesn't depend on scales or what the measurement outcomes are, whether you measure them in centimeters or whatnot. So it's really something more basic than this, and it's also something more natural for an informational perspective. And anyway, within such a setup, there will be the rules that will impose some rules on information acquisition that will single out quantum theory within a certain landscape. And so these are the axioms, basically. In colloquial form, there's an information limit that basically a composite system of n qubits or ng bits, if you want, generalized bits, carries at most, or that the observer can acquire at most n independent bits of information about these systems. The second one is we will posit the existence of complementary information, or complementarity, really. The third one is really, you can view it as a definition of a closed system if you want. We'll just require that the total amount of information is preserved in between interrogations. And the fourth one is, in some sense, that any consistent time evolution is allowed, and also that any question that makes sense or that gives you consistent probabilities is also physically realizable. And what I should say is that it's kind of broadly inspired by some earlier works, but it also differs from those. So this is kind of broadly the context in which we were going to be operating. And now let's just look at a naive comparison, and in particular, in terms of the axioms, how intuitive they are, or whether they're simple. I know you may say, well, I haven't actually told you about what these axioms mean technically, so how can I compare them? But I've actually also not told you what I exactly mean by that statement. So this is a qualitative statement, and I can compare them at this level. And now, when you first of all look at it like this, oh, here's one principle, and there's 5. It looks kind of bad, and that's what you sometimes then, I guess, also hear, that we don't have as convincing a reconstruction as a derivation of special relativity from the relativity axiom. But really, the situation isn't quite as bad as that, because it's a misconception that this relativity principle actually singles out special relativity in Minkowski space. In particular, that principle is also true in general relativity. It's true in a whole continuum of spacetimes. In fact, an infinite dimensional field space will satisfy that. So it's really not at all, singling out special relativity. Now we have to do a little bit more if you want to get special relativity in Minkowski space. And you will need at least the following. So we first of all need that space is actually 3D Euclidean. So the dimensionality of the space is an input. You don't get that from the relativity principle, and also not that the space is Euclidean geometry. We have one time direction, not two. You could in principle formulate special relativity also in more time directions. We need that Newton's first law holds, so we can actually talk about inertial observers. They define inertial observers. Inertial observers are those in which free particles move on a straight line. Well, then we have the relativity principle. In fact, even the relativity principle has a little bit more information in it than what's usually assumed. It's not actually all the laws of physics, because gravity is in fact not relativistic in the Newtonian form. And if you want to include gravity, then you actually have to go to general relativity. So it's we have to be a bit careful with that. And there's also another axiom that you will need if you really want to recover the full set of inertial observers and the full Poincaré group. You have to also impose some kind of unrestrictedness that basically every consistent inertial observer is allowed. And so when you actually look at it from that point of view, the situation doesn't look that bad anymore. Whether it's the same is a separate question, but I just want to put that into perspective, that the situations with reconstructions aren't quite as bad as sometimes is assumed. Now let's think a little bit more about these axioms. So when you look at what you need in special relativity, these 4 in blue, they're actually all true in Newtonian physics as well. And that's clearly, that means the juice of special relativity is in the relativity principle. That shouldn't surprise you. That's why, of course, we focus on that relativity principle when we think about how we get to special relativity. And now, when it comes to this reconstruction of quantum theory, it's a bit similar. You also have 4 axioms that are basically true in classical bit theory. So remember, we're actually talking about a generalized bit series. And so we should compare it to classical probability theory for bits. And the reason I put that into a slightly different color is I haven't really told you what I mean by consistent time evolution. I will require in the end that it's continuous, and that's not true for classical bit theory. So up to that continuity, it is true. But basically, what that just means is that what you mean by consistent time evolution, in a classical bit theory or in quantum mechanics, you have to adapt that. But otherwise, these axioms are true, also in classical bit theory. And similarly, it's then the complementarity principle that's really encoding all the juice about quantum theory. And in fact, it's really where quantum randomness sits in. So that's really basically the core principle of this axiomatization. Now, let's maybe, we went from the relativity principle and then spelled out what additional ingredients we need. Now let's deconstruct that a little bit again. So when you compare, for instance, this axiom here, that every inertial frame is somehow allowed, and then here every consistent time evolution is allowed, and any question that makes sense is allowed. These are sort of unrestrictedness axioms that are simply necessary if you want to, and that's nothing special to special relativity or quantum theory. It's just something that at some point you will need if you want to get the full set of possibilities that are compatible with a certain axiom. So if you want to get the set of all inertial observers, the full Poincaré group, or in quantum theory, want to get the full unitary group, the full state spaces and so on, at some point you have to assume something like this. But because of that, these 2 axioms here, they should be viewed in the same sense as that. They're really nothing particular about quantum theory. So that's, take that in some sense as a given. They're not innocent. You need them to get the full formalism, to get the full set of possibilities. But they're really nothing special to quantum theory. And then you should compare rather, the surviving set of axioms as being more about what the theories are about. Now, if you look at the first one, is information limits. This is actually a restriction on the type of systems and not on the type of theory, meaning we're looking at bit systems rather than, some continuous, whatever, mechanical systems or so. So it's more like a definition restriction of what we're going to consider. It's of course not the most general derivation of quantum theory in that sense, but it's you have an additional restriction, and in some sense, the type qualitatively these axioms are not exactly of the same type as this here, but they're kind of a restriction on the dimension and also on the topology of the geometry, but not on the type of theory. You can formulate special relativity in the cylindrical space. For example, you can formulate special relativity in 150 plus 1 dimensions if you want. That's all possible. And now, so let's take these out for the moment, as also not, they're not so much about the theory, more about a concrete realization of the theory. Now, if you look at this last one here, that the total amount of information is preserved in between interrogations. That's basically just the definition of a closed system. So, you can take it as that. And in some sense here, when it comes to Newton's first law, we could basically just take it as one of the laws of physics and integrate it here in some sense. So we're of course ending up now with basically the 2 core principles of the theory, that I mentioned before. And so it's not a surprise that we end up here. But I just want to give you a bit of the logic and the flavor of how you should think about some of the types of axioms that we're dealing with here. And the important thing about these 2 surviving axioms is that they're empirically falsifiable. The relativity principle and the constancy of speed of light that was, after all, tested in the Michelson-Morley experiment, and the existence of complementarity of information is an empirical fact. There's a double slit experiment, particle-wave duality, different measurements in different spin directions and so on. That's just an empirical input. And so that's part of the axiomatization here. Okay, now between these different axiomatizations of special relativity and quantum theory, there's also another type of similarity that's maybe worthwhile to mention. One of the reasons I think that we find special relativity maybe not so counterintuitive after we accept the relativity principles that it does involve a lot of classical structure from Newtonian physics that we kind of take for granted, right? So we have space is 3D Euclidean, and that remains also in special relativity like this. And what does special relativity do? It basically takes some older absolute structures, such as the absolute Euclidean 3D space, and kind of multiplies them into something that's no longer absolute. And then it kind of sews them together using the core principle. You know, the relativity principle is ultimately what gives you the Lorentz transformations and the Minkowski metric. And that's, after all, what kind of puts consistently together these different kind of classical notions that we were familiar with before special relativity. And something similar happens also in quantum theory. And here you can think about it that classically we have something like an absolute measurement context, if you want. So we kind of use classical logic to reason about the world. There's no restriction on how many things we can measure, at least in principle, at the same time. And in quantum theory, that's of course not true. We get non-trivial measurement contexts. They're no longer absolute, but they will become soon together in non-trivial ways using the algebra of observables. And that's, at the end of the day, kind of also implied by the notion of complementarity. So there's some, in that sense, some similarity, and I will come back to that a bit later. So that's just to mention at this qualitative level. I'm not saying that the situation is really the same on the two for the two theories, but comparing the quantum theory axiomatization with special relativity is actually a situation that doesn't look quite as bleak as sometimes is assumed. And one other thing that is worthwhile to mention is that, for instance, in these constructions of special relativity, really, it's when you think about the spatial geometry, the space-time dimension, and spatial symmetry, they're inputs into the derivation. In quantum theory, the dimensions, the symmetries, and the geometries of the states and observable space are an output. So in some sense, you can even argue that, and that doesn't apply just to this reconstruction I'm talking about, but all of the reconstructions, that they're arguably coming a much longer way than the reconstruction of quantum theory. So that's another thing you should put into perspective in terms of what they achieve technically. It's possibly actually a bigger task than the derivation of special relativity from those axioms then. Okay, so now let me talk a little bit more about the type of reconstruction that I've been involved in after this qualitative discussion. So I just wanted to do that to put that into a broader context before we go now into a little bit more detail into that reconstruction. So what we want to do now is basically build quantum theory from scratch. So we want to define some landscape of alternative theories. And here it's not going to be GPTs or any of these other landscapes that have otherwise been used. We want to formulate some axioms that signal out qubit quantum theory within that landscape. And depending on how it goes with time, I may give you a glimpse of the derivation of some of the formalism, at least a taste of it, in basically the architecture of the theory, state spaces, unitary group, projective measurements, Born rule, and so on. And now we will come back to that wish list here that I discussed before later. Let me just mention, so basically that comparison we've already done. Is that a success or not? I don't put a very strong green hook here. Maybe also a question mark, because, whether you think it's as simple or not, or as intuitive, that is for you to judge. The main point I wanted to make is that, the comparison between special relativity and quantum theory axiomatization is not as bad as it seems, or as lopsided as it seems at first. Okay. Now, let me tell you a little bit more about that reconstruction and its basic ingredients. And so, as I already mentioned before, we're going to consider basically the information acquisition of some observer about some system or ensemble of systems. And we have an operational premise that we only want to talk about the information that the observer has access to, that they can test in interrogations, basically. And so the setup is here, we have the observer interrogating the system with binary and, in fact, repeatable questions from some set. And now I will define that landscape. So the landscape will be defined by a set of axioms too. I call them here assumptions. And okay, one of the basic assumptions is that the system, gives answers to these questions. So in the sense of there will be a definite outcome. So it means in particular, just as a disclaimer, I'm not going to address the measurement problem. And then there's a couple of basic ingredients. First of all, there's some set Q of these binary questions that O is allowed to ask the system or that make physical sense, that are physically implementable. And we also think of the observer as some kind of agent who's allowed to do statistics, and they are allowed to do repetitions of interrogations and preparations. There's a notion of identical preparation and so on, and so they can do statistics over the answers to different questions that they may pose to ensembles of systems coming out of the preparation device. And there's some set sigma that basically is, in some sense, the set of all possible answer statistics for every question in that set that they're allowed to ask, and in fact, every mode of preparation. And now, the next assumption is that O has a theoretical model for these two sets here, by means of which they reason about the world. And our task is, based on additional ingredients, to kind of single out or to determine what that model is. And now we will take a somewhat broadly Bayesian viewpoint. I say broadly because I don't really go much into the details of Bayesianism here. And the basic idea is that for a specific system that is coming out of the preparation device next to the observer can assign basically prior probabilities to the outcomes of all the questions that they may ask to that system, and that is modeled according to whatever information they have about this particular S or the particular preparation method, and the set sigma, in some sense, the space of all possible answer statistics. We don't really have to say very much about how exactly they assign these probabilities. We'll just assume that they have a way of doing that. And then the other thing is that we want to say that now all these probabilities are really everything that the observer can say about the system. And so in that sense, we can identify the state of the system with that set of probabilities. And if we do that, then it's natural to actually identify the sigma, the space of all answer statistics, with the state space. And for operational reasons, we'll assume that it's a convex set, so that the observer is also allowed to do coin flip scenarios. Depending on the outcome of a coin flip, they will ask, a system prepared that way or a system prepared that way, instead of a probabilistic description of that. And now, and also, if we view the probabilities here, in this way, then it's also natural to view the state as in some sense, a catalog of knowledge about the system, or it's an informational state, if you want. And now I will introduce a little bit more structure. So there's a bit more kind of background ideas, how you should think of that landscape. But now I want to impose a bit more structure onto it. And I want to impose the existence of a special state. Operationally, we would like to have the situation that there's a state where the observer is allowed to have no information whatsoever about the system, meaning that all the probabilities they assign to all the questions as a prior is just 1/2. And that's actually a restriction both on the set of questions and that state space. And the reason I want to impose that existence is because I want to introduce some structure on the set of questions in terms of independence relations. And in order to define independence of questions, it's in general actually a state-dependent relation. And so if we have a preferred state, then it's kind of more natural to define independence relative to that preferred state. In particular, if you think about it as, basically building up relative to a state of no information, and you think about it in terms of an information updating. And another thing we shall assume is that O has some consistent state update rule, and so that they can do some state updating. Okay. And I won't tell you much more about this. There's not really, there's some minor additional assumptions on the update rule, but you can ask me later if you want, but it will take us too far now. But now we want to use that structure to define some relations for two questions on from such a question set. And so we will define them to be maximally independent if relative to the state of no information, this kind of preferred state that I just posited exists, if relative to that state, the answer to only the first question gives no information about the second, in the sense that that after only asking Q1 and use state updating, the probability of the second question is just 1/2, and vice versa. And so as an example, for 2 qubits, you have that, for instance, the spin of qubit 1 and 2 along x direction, say, they're independent in that sense relative to the completely mixed state. So the state of no information will be the completely mixed state. Now, we can also define 2 questions to be maximally compatible if they're simultaneously knowable. So if they exist a state such that the corresponding probabilities are simultaneously 0 or 1, and well, you can take the same questions as here for 2 qubits and then look at a product state, say. And we can also define a notion of complementarity. And we just define these 2 questions to be maximally complementary if having maximal information about what, let's say question 1, so probability is 0 or 1, necessarily implies that the probability of the second is 1/2. And in fact, we require it to be symmetric. And well, for a single qubit, it's like spin in x and y direction or so. Okay, so now before I said we are parametrizing or describing a state of the system or an ensemble of systems relative to O by the set of all these probabilities. That's of course not very practical. And so we want to constrain that a bit. And the assumption that we impose is that any maximal set of pairwise independent questions, in the sense that you have a set of questions, they're pairwise independent, and I cannot add another question to it without destroying pairwise independence, that any such set is informationally complete, in the sense that the probabilities describing the outcomes to those questions, in fact, imply the probabilities of every other question in the set. And then if we do that, that means we can parameterize the state by some probabilities. I don't tell you how many of them, and that's something that the reconstruction in the end has to single out, but it's just the vector, basically. And now, since we're talking about information, we also should say something about how we quantify information. I just impose at this moment just a very basic restriction on it, that the observer's information about some question Qi is just some function alpha of the corresponding probability Pi only. And this is bounded by 0 and 1 bit. And we make the ansatz for the total information that the observer has about the system to be basically the information contained in the questions in an informationally complete set. So you just basically add up the information that the observer has about the questions in an informationally complete set. And now let's come back to this thing that I mentioned, where also in the quantum theory, we basically have also, we kind of multiply a previously absolute notion, in this case of kind of an absolute measurement context. And now how do we generalize that? And then quantum theory in the end should sew that together. And basically here it comes down to essentially this question, that this assumption or permission that classical rules of inference in the sense of Boolean logic apply only or exclusively to compatible questions, maximally compatible questions. So in the sense that if I have 2 questions and I have some logical connective, they're implementable only if these 2 questions are maximally compatible. And now we can use this notion also to come to a notion of composite systems. At the end of the day, we want to talk about composite systems of generalized bits or qubits in the end. So I have to tell you what I mean by a composite system. And you define that in terms of the sets of questions that the observer is allowed to ask them. So we need to be able to somehow, here's a composite system, and the observer has to be able to somehow decompose that somehow logically into its constituents. And basically, the definition is that the corresponding question set is basically the union of the questions of the individual subsystems, plus the union of all the logical composites of questions from the two, in such a way that, and in particular, what we assume is that all the questions in here are compatible with and independent of all the questions here, so you can build their logical connectives. But you're also allowed to build other connectives of, of even composite questions of these. I mean, you're allowed to build composite questions as long as they're compatible. And now, one last thing about time evolution. So we don't really make a big assumption. So it's just that states are allowed to evolve in time in between interrogations. And that just means that the state vector P can change in some way under time evolution corresponding to some time interval, will require translation invariance. And the only requirement at this point is that the image under time evolution of the state vector is again, in the state space. And then the set of all time evolutions we denote by this T. And now, so that's basically, in some sense, the landscape, a summary of it. And now our task is to figure out what's O's theoretical model for these structures here, the set of questions, the state space, and the set of time evolutions. Okay, so now we come to the rules or the axioms actually that we want to. So now we have basically, I've given you a summary of how to define that landscape. Now we want to find the axioms that single out the blue dot. And the first one is this limited information that I mentioned before. So I'll first give it to you in colloquial form in red, and then in the more technical form in black. So the statement is that O can acquire maximally n independent bits of information about the composite system of n g bits at the same time. And so what we want to say is there exists a maximal set of n mutually maximally independent compatible questions. And in fact, there exists no set with these compatibility and independent structure with more than n elements. Okay. Now let's go to the second one. So this, of course, also holds for classical bits. And now the second one is complementarity, and it's basically I just require that there exists complementary information for a single g bit. So for the n equals 1 case subsystem, there exists some q1 prime that's maximally complementary to q1 that might have been in that set. And just for your information, in case you look at all the papers that have been written about this reconstruction, this axiom here differs from the ones that are published. Turns out that it's not equivalent to the other one that is there in place in the articles, but it's a weaker one. So the one that's published is stronger. It implies this one, but this one is weaker, but it still does the job. And so it's a nicer one. So I put it here, but it's not the one that's in those papers. Then the third one is preservation of information, that the total amount of information that O has about the system is preserved in between interrogations, no information leakage. So you can take that as a definition of a closed system, really, if you want, as I mentioned before. And so all we want to say is that the total information that I defined before is constant in time in between interrogations. Of course, it doesn't mean that the state can change. It's just that that measure there is constant. And now, as I mentioned before, it's basically these three axioms are kind of the core of the quantum reconstruction. The next two are these unrestrictedness axioms that are you should view in the same sense as an unrestrictedness axiom in special relativity to get the full Poincaré group. And I won't be using them in the rest of the talk, so I'll just give you the colloquial form. And that's basically O's catalog of knowledge. The state evolves continuously in time. in between the interrogations, and every consistent such evolution is physically realizable in the sense that it, as long as it abides by the other axioms. And 5 was this question unrestrictedness, and always allowed to ask any question that makes probabilistic sense, gives consistent probabilities. And now it turns out when you have these axioms in that landscape, it basically has 2 solutions, and these are qubits and rebits. And so that's just quantum theory over complex numbers and quantum theory over the real Hilbert spaces. And so these axioms cannot distinguish between that. So if you want to kill rebit quantum theory, then you just impose another one. That's local tomography. That's actually a very strong axiom. It's much stronger than what I need it for. So it's in some sense redundant for this reconstruction. People in the GPT framework use it all the time for reconstructions. It's the statement that the observer can determine the state of a composite system by only interrogating its constituents. It implies a lot of structure actually in the GPT framework, but here I really only need it to kill the real quantum theory case. And why is that actually the case? Because for real quantum theory, it's basically the observables are something like Pauli matrices over, or symmetric matrices over real Hilbert spaces, and Rn essentially. And you can think about it, if you look at the Pauli matrices, sigma x and sigma z, they're both real, they're observables, but sigma y is not, because it has I inside. Now, when you think about 2 rebits, and you look at tensor products of the Pauli matrices, then you can look at, of course, all the tensor products of sigma x, sigma y, and the identity, sigma x and sigma z and the identity, but you're not allowed to look at something like sigma x tensor sigma y. But you get a new question, which is now sigma y tensor sigma y, because then the i's cancel. And so you get actually a composite observable on the real Hilbert space, sigma y, that has no individual counterpart on a single rebit Hilbert space. And but it yet is an independent observable. And if you want to determine the state in general, you have to do a non-local measurement, sigma y. And that's why local tomography actually kills that case. Okay. So I had not mentioned that local tomography axiom before, in this early qualitative comparison, and that's because basically the real quantum theory case is mathematically contained in the complex one, and you can also actually simulate them in a lab. So in some sense, they're consistent with this world under certain restrictions if you restrict the complex quantum theory. So and that's why for me, basically the first 5 are essentially what does the job. But mathematically, if you want to kill the rebit case, then you impose this. And now then afterwards you can show that the sigma n, so it's now labeled by these n's here, is just the set of density matrices for n qubits. The set of all possible time evolutions is just PSU 2 to the n. So it's basically conjugation by unitaries with arbitrary unitaries on a 2-qubit Hilbert space, and states evolve according to the von Neumann equation. And the set of questions is the set of Pauli operators, where a Pauli operator is just one that has equally many plus and minus 1 eigenvalues. And probabilities are computed according to Born rule. We started 10 minutes late. Okay. Okay. Is it really 5 minutes? Because 5 minutes will be difficult, and I have no idea what's happening now, because we started 10 past, I think. I don't know what's happening now. I'm sorry, I don't know what's happening here, and with Zoom, somehow you can't see the mouse, and so I can't click that away. Let me go on. I hope nothing worse happens. Or am I out of the Zoom now? Or? I'm in Zoom, okay. Okay, so should I try to log in or go on, or?
You should just go on. I think it'll wait a minute.
Okay, anyway, so now as a first reconstruction step, you have to basically build up these informationally complete sets. And how do you do this? Let's start from a single qubit or a single G-bit. And so we have some questions, and basically the complementarity principle tells you, well, you have multiple ones of them, and at least two of them, and they will be complementary. And now you can represent that for a single G-bit, these questions by vertices if you want. Now, when we do two G-bits, you have, of course, also the other individual questions for the second G-bit. But now we can also build composite questions that we can denote by vertices, for example. And what we want is that these composite questions, because it's supposed to be an informationally complete set, so they have to be pairwise independent. And you can convince yourself that pairwise independence requires that the composite questions are given by an XNOR or an XOR. So meaning that basically they stand in for the question, are the answers to, for instance, QI and QJ, are they the same? And you can, because you're only allowed to build connectives of compatible questions, you can't build edges here on one side. They have to be in between the two sides. You can build all these edges. And then you can convince yourself that the two rules, the information limit and the complementarity principle, imply that these edges here, they're actually pairwise independent. They're complementary if the corresponding edges intersect. So for instance, these two here are complementary, and they're compatible if the corresponding edges don't intersect. So Q11, Q22 are compatible, and they're compatible with individual questions if the individual question is a vertex of such an edge. Okay, and now we can use that structure to come back to one point on the wish list, is whether we can also explain counterintuitive phenomena intuitively of quantum theory. And let me just explain how we get entanglement. And that's from what we've just seen. So we have that Q11, Q2 are actually compatible, and they're pairwise independent. So it means the observer can actually ask both of these questions together. But there's an information limit. So it means actually O has spent their entire information budget by asking these two questions. And these two composite questions are only compatible with an individual one if that's a vertex of that question. But that means if I have two of those, no vertex can be, is jointly a vertex of the two. So it means I cannot have any individual information at the same time. And that's really just entanglement. So it's implied by complementarity. And so really in the sense that the best possible knowledge of a whole does not necessarily include the best possible knowledge of all its parts. So in the very sense in which Schrödinger defined entanglement. And a state like this is really corresponds to Bell states. Now you can also just give you a brief intuition about monogamy in this case. So suppose we have now that two qubits A and B are maximally entangled in the sense in which I just described it, that the observer has spent maximum information about these two, has the answers to these two questions. The information over these two questions, these two subsystems are already spent. We fit the information limit. And so the third independent bit that they can spend on the total composite system should not reveal any new information about the subsystem AB. So in the sense that this should be, the additional bit can only be an individual property of that system C. So this is kind of heuristic, what I'm giving you here, but you can actually make that rigorous using the compatibility structure. So in that sense, you get also that monogamy is implied. Okay, for some reason. Okay, yeah. Yeah, so and in fact, you can do something similar with non-locality. And I'm sorry, the slides don't move. So in some sense, when you look at the wish list, is it realized? I'll give it a slight superposition of yes and no. So there's clearly some nice informational explanation from very basic principles of these counterintuitive phenomena. but is it as intuitive as getting relativity of simultaneity from the relativity principle? Not quite, because in that setting, this example with a train, I didn't really need to use any really quantitative structures to come to that conclusions. But whereas here, I needed to talk about compatibility and those kind of structures that I have to first prove. So I'm going to skip this. It's about what's the dimension of the Bloch ball. You can have a very cute argument for why it's at most three-dimensional. One thing is that, that's important for something else that I want to say is you can actually show also from these axioms that the information measure is given by a quadratic measure. And basically it's given by the total information by the square length of the Bloch vector. So the Bloch vector is just given by 2 times the state vector minus a vector filled with ones. And this is this Bruckner-Zeilinger measure that has been proposed by them from a slightly different perspective. Here it kind of comes out of this formalism. So it tells you, for instance, that in some sense, that the Bloch vector length squared is equal to the number of answered questions. That also tells you, together with the preservation axiom, in between that time evolution has to preserve the total information in between interrogations. That means then, of course, that it has to preserve the Bloch vector length. So that means any time evolution has to be some kind of subset of SO dn, where dn is the state space dimension. And now let me come to very quickly to this thing about on the wish list about new predictions and structural insights, whether it can come out from a reconstruction as well. And in fact, it does in this case. Let me start with a trivial case that's not really a new insight, but that will make it more intuitive what happens. So if we have a single qubit, we can actually get a maximal set of mutually complementary questions. It's just given by 3, Q1, Q2, Q3, 3 questions that will basically correspond to X, Y, Z. That comes out of basically the axioms, the information limit, complementarity, and also local tomography. That has to do with the dimensionality of the Bloch ball that I kind of skipped that part. And now from the information limit, I know I can have up to 1 bit of information about a single independent bit of information about a single qubit. And I have that the total information is given by the Bloch vector length. And so I can define basically pure states as being states of maximum information that are that satisfy this relation. And that's a conserved informational charge under all the time evolutions. And yeah, it's a complementarity identity for pure states. These correspond to maximally complementary questions. The more I know about this one, the less I know about the other questions. So in that sense, it's a complementarity identity. It's not an inequality, it's an equality. And it tells us that the maximal set of mutually complementary questions carries exactly 1 bit. And then basically using this, you can, using the axioms, basically argue that, you pick out one natural state and then you apply, time evolution. So you can argue that every consistent evolution allowed, you get to the SO3 and then you get the full Bloch sphere, and by convexity, the full Bloch ball. And let me maybe this as a last topic. So, what I just said is kind of, that's not new, but now the somewhat new insight is here on this slide. You can ask, how can I generalize that to more than 1 qubit? So this kind of informational charge that I had on the previous slide was core for actually defining what's the set of all possible time evolutions and also defining the set of pure states. And can we do something similar for 2 qubits? And here it turns out from the complementarity relations and so on, you can show that there exist now 6 maximal sets of mutually complementary questions, and they contain now each 5 questions, and you can represent them by these pentagons and put a tessellation together. And now it turns out that you can also show from the axioms that each of these pentagons carry exactly 1 bit of information. And in the following sense, and only for pure states, I should say. It's only true for pure states. And these are also conserved under time evolution. You can prove that. And so, for instance, for the pentagon 1, you take the 5 questions here, and you look at the Bloch vector component, square them, and it has to be equal to 1. And so in quantum theory, it would take that form, for example. And so that's another, pure state complementarity identity. You have a maximal set of mutually complementary questions, and it carries exactly 1 bit for pure states. And these are actually, so as far as I know, they were not known before, these relations, and they're actually quite nice because they also determine the space of pure states and the unitary group. And basically, a set of pure states is the set of Bloch vectors that satisfies these relations, plus another conservation condition. And the unitary group, you can read off the generators from this diagram here. And for example, because by construction, the unitary group has to preserve these identities, you can ask what kind of transformations can I have? And you can see that there exist exactly 15 complete swaps of information. And for instance, these red arrows indicate one of those. Here I'm swapping the information that's contained in this question and that question. That happens within a pentagon. So if I swap them, I don't change the information content in that pentagon. If I swap the information here and here, the two are actually also in one pentagon because that question is also here. So I preserve the information in that pentagon and so on. You can convince yourself that that's also true for these here. And I can do this for any pair of these 6 pentagons, and you get 15 of those. And when you write them out in component form, in the end, you find that they're exactly the 15 generators of PSU4. And in this way, you can read off basically what the group is. I'm gonna skip mostly what I have here. I just want to say that this is something new that will be appearing soon. So this was only for 2 qubits, what I showed you now. It turns out for the reconstruction, it was unnecessary to know what these complementarity identities are for arbitrarily many qubits. But a natural question is, of course, what are they? And that's something that we've now finally figured out. And in order to do this, you have to go to a more general notion of complementarity sets, where you now don't have just individual questions being complementary with one another, but entire sets of them. And so that leads naturally to this notion of mutual unbiasedness. And anyway, I'm not going to go into the details here. You get new identities for pure states that you can actually generate from mutually unbiased bases. If you want to know more, you can ask me later. And anyway, here's, for instance, for 3 qubits, you get 28 such pure state identities that each carry 3 bits. And this here, for instance, is all the operators in 1, and you have 28 of those. So you can actually derive all of that. And so that's something that comes out of this reconstruction, basically. Okay, so here's a emphatic green hook. And now the interpretational part I skip, so I have some things to say on that. What does it do about interpretation at face value? Doesn't fix it, but it does give you a partial insight. If you want to know more, you can ask me later. So it's kind of a superposition of yes and no. And I conclude with that wish list and basically the conclusions from this talk, and I'll let you read it. Thanks for your attention.
Great, thank you very much, Philip. So we have perhaps 10 minutes for questions. Rudiger?
Well, thank you for this nice talk. So your first bit of your wish list mentioned intuitive and simple axioms. Now, I mean, something that you find intuitive, I might find counterintuitive. Something you find simple, I might find. But so, I mean, why even mention them? I mean, there's there's many different ways of writing down these axioms. So these 2 criteria cannot really distinguish them, or can they?
Which 2 criteria?
Intuitive and simple.
No, sure. I mean, I totally agree. I mean, and your point. I mean, that's why I write here. Depends on the eye of the beholder whether you think that's satisfied or not. I mean, I totally agree with you, of course. The reason I did bring that up is because people sometimes complain that these operational reconstructions of quantum theory, operational axiomatizations have axioms that are much less intuitive than, or much more complicated, assuming much more structure than in a context of special relativity. And so my main point here is not that, that's why I also put a question mark there, whether we have achieved that it is as simple or as intuitive. But the main point is more that, this comparison, that there's a lopsidedness, and, the derivation of special relativity from the relativity axiom is just so much simpler and more intuitive. It's just not true. You have to put that into a larger perspective, and the situation is not that bleak, actually. And I personally find it's quite, it's qualitatively fairly similar, actually. But I totally agree that, whether you find it as nice or simple, it's very subjective. Yes, of course.
So if you find it intuitive, is it that special relativity becomes intuitive for you with Minkowski space? And the second question is, what I always ask, how is it possible that Lorentz first derived the Lorentz construction time dilatation from the ether concept, and then Einstein can drop the ether, take the Lorentz construction, and put it in the Minkowski space? For me, it's not intuitive at all. Maybe you can explain this a little bit.
What is that intuitive at all? That Einstein dropped this, or
Einstein dropped the ether, but Lorentz derived the time dilatation and the Lorentz construction from the ether concept. So what happened there?
I mean, okay, I must admit, I don't remember the derivation of Lorentz. But I personally find, I guess we're getting into subjective territory now. But starting with since you were asking about Minkowski space, doing a mathematical axiomatization of special relativity, here is Minkowski space, there's Minkowski metric, and now you look at whatever observers are time-like curves in that, and so on. That's, to me, more or less the equivalent of doing textbook axioms for quantum theory. So it's mathematically defined, but not very operational. Why should it be like this, right? So something that's intuitive for me, or much more intuitive, is if you indeed start from this more operational perspective that Einstein brought to the game by really talking about observers, what they're allowed to do, what they can do, their interrelation, things that are empirically testable, and then actually deriving, the structure of the theory, and then you see, okay, maybe Minkowski space is a good description. You could, of course, say, well, there are inputs such as spaces for every observer, every inertial observer, 3D Euclidean. I mean, that it's three-dimensional, okay, it's kind of empirical. It's Euclidean is a good approximation. There, of course, there's some fine print there, but at least it's not just the full mathematical axiomatization. There's really physical argumentation involved, and so I find that much more valuable from a physical point of view.
How about Q-tricks?
Yes, that's a good question. So, or arbitrary n-level systems. So we didn't cover it here. So there's one very simple way out, but it doesn't fit naturally into this program, which is the subspace axiom by Hardy that he imposed, for instance, in his first derivation of quantum theory from these 5 reasonable axioms. And the subspace axiom is basically, if you have an n-level system and you restrict it to n-1 levels, then the state space is, the resulting state space is the same as that of a genuine n-1 level system. If you impose something like this here, you can basically get any level, but it's not something that seems very natural in its philosophy to fit into this. So if you really want to include them in the same conceptual scheme, then you have to do something else, and that means you have to move away from basically binary questions. So binary questions are naturally geared to qubits, and so you would have to go to basically questions with whatever any prime number of outputs. And I'm pretty sure you can do it. This took 3 years to do, more actually. I just didn't do it. But for me, that's more, I think, a technical problem than a conceptual one. I would be quite confident that, this should work basically the same way.
I think prime powers are probably okay.
Yeah.
But how about composite dimensions? Because there you would learn interesting things, for example, about mutually unbiased bases.
Yeah, that's right. So here, I'm also looking at composite systems, right? I can also at the end build composite systems of a 3-level system and a 2-level system. Once I include any prime number of levels, I can do that. And then you're right, with mutually unbiased bases, then I get into all kinds of troubles. And I guess for 5-level systems and so on, there are some open questions and so on. But I don't think that this is completely necessary for the derivation per se. So this mutual unbiasedness that I was talking about very briefly at the end for these new informational complementarity identities for pure states, that's actually don't need it for the reconstruction. You could use it, but you don't necessarily have to.
It would be interesting to see how far you get.
Yeah, sure. Yeah, I agree.
Thank you.
Okay, so this is the last question.
So I can see a faded red cross next to the third point, but I'm interested in if you can speak anything about the interpretations based on your reconstruction.
Yeah, so that was the slide I skipped. So, I don't have a lot to say about it, but I have a couple of things to say. But so basically, I'm allowed to do the last slide. So basically, the statement is that the reconstruction that I presented very briefly by itself, does not rule out any interpretation at face value. So in that sense, you can say no. And that's just because here, we only talk about the information that is accessible to an observer, but we don't say where this information comes from. We impose rules on the acquisition of information of the observer about the system. We never say where these rules come from. Do they come from some underlying ontic model or some underlying reality? I just don't say anything about it, right? But I'm not ruling them out. And in fact, this is really, again, also rooted in the axiom that really encodes the essence of quantum theory, namely complementarity, quantum randomness. And then ultimately the question, is there some missing information or not, in quotation marks? And that's, of course, where all the interpretations will disagree on, basically. And I just don't say anything about whether there's something missing or not. And now, why the partial green hook? It does at least suggest a partial interpretation. And in the sense that you can get the textbook formalism, you basically get it as some kind of universal rule book for, to reason about the world or to acquire information about the world in the face of, in some sense, necessarily incomplete information. Why do I say universal? I didn't tell you anything about how these qubits are physically incarnated. Are they quantum dots or spins that have a spatial interpretation? And yeah, it's only, it is sufficient to speak only about the information that the observer has or that they can test. And it gives you an informational explanation for the architecture of the theory, and I never need to talk about anything like an underlying reality. So in that sense, it gives you a partial interpretation of the formalism. It's kind of a law book for observers to acquire information about the world. And then whether you make that now with relational quantum mechanics, cubism, or whatever, that's something that this won't tell you anything about.
Thank you.